Welcome student in today's online section of subject mechatronics. Today we are going to see another concept of chapter number 5. So we already see about this PID controller, then proportional controller, proportional plus. So today we are going to see about this parallel form of PI control. PI controller means proportional plus integral control. So here what is this proportional plus integral control? Here you can see on your screen. I will show you. So here you can see it is a proportional plus integral control. Okay. So here you can see this K of P means it is the proportional controller. It is fitted here along with the integral controller having function Ki upon S, and they are connected each other with the parallel way, and this is the feedback loop, and the error which is coming after this setting point here, this error signal is went to the proportional controller plus integral controller, and then both output of this comes at the summing point, and then this control signal is sent to the plant here. Okay, and we will get the output signal. Output signal is again sent to this setting point via the feedback loop. Okay, so here it is the block diagram for this proportional plus integral control. Okay, so now we are going to see about some control function or advantages of this proportional plus integral control. So here we are. Here the transfer function can be calculated as Kp plus Ki upon S, where Kp it is the proportional gain and Ki it is the integral gain. Here the output will be the output is u of t, which is equals to up of t plus ui of t, which can be written as Kp into e plus Ki into integration of e of dt, where e it is the error and t for the time. Okay, so the proportional integral controller produces an output. So u of t it is the output, which is combination of output of the proportional and integral control. So here it is clear. The transfer function of proportional plus integral, it is the transfer function h of s, which is equals to Kp plus Ki upon S. The proportional integral controller is used to decrease the steady state error without affecting the stability of control system. Here controller output is fixed at specific value when error is 0. If the error is not 0, then integral term increases or decreases depend on positive or negative value of error. So here you can see it is the positive value of error at this focus on this point. So this overshoot is reduced here. So here controller output is fixed as specific value. So it is the fixed value. So these are the controller value which are also fixed, but on depend on this error, as this moving upward and downward, this is the error. So if this error is positive and negative, then integral term increases or decreases. So here it is the integral term which increases for this positive error and it is decreases for the negative error. This is the error signal, and this is the output of the PI controller. Proportional mode alone not capable to reduce the offset in error, so integral mode used to eliminate the proportional offset. As we already studied that the main disadvantage of proportional controller is that it is having an offset. So to eliminate this offset, here we are going to use this integral controller along with the proportional controller. Now we are going to see this parallel form of PD controller, means proportional derivative controller. So here you can see this block diagram of this proportional derivative controller. Okay, so here on your screen you can see this is the proportional plus derivative controller. Here along with this proportional controller we are going to add the derivative controller, which is KD here, transfer function, and this error which is coming from this feedback loop is then sent to the proportional plus derivative controller, and after the output signal will be the summation of these two, which is coming from proportional controller and derivative controller, and then this control signal is then sent to the plant, and this process again continue. So here you can see this transfer function of this P plus D controller is Kp plus Sk of D into E of S. Okay. Advantages of this PD controller: it is a maximum overshoot decreases and delay time increases. Steady state error remains same. These are the advantages of this PD controller. Here transfer function h of s is equals to Kp plus Kd into S, where Kp it is the proportional of gain and Kd it is the derivative gain. The output of this two controller, output of this PD controller will be up of t plus ud of t, which can be written as Kp into E plus Kd into ddt of E. It is the derivative function and this is the proportional function. The proportional derivative PD control helps in reduces the rise time, setting time, as well as minimize the overshoot. Here you can see how many how the very large value of overshoot is available here, but after applying the PD control the overshoot size is get reduces here. Again it helps to reduce the rise time. Here you can see the rise time is also reduced here, and setting time also. Now we are going to see the effect of this PID on transient specification. Okay, the proportional term is the action Kp. Initially we are going to study this proportional term. It provides an overall control action proportional to the error signal throughout the all pass gain factor. So after applying the proportional controller here, what will be its effect on the rise time? Its rise time decreases, overshoot increases, setting time will be the small change, and error also decreases there. Then what is the application of this integral term? It reduces the steady state error through low frequency compensation by an integrator. So here after applying of this integral controller, the rise time decreases, this overshoot increases. This is the disadvantage of this integral controller. Then setting time, the setting time is initially decreases, then it increases, and the steady state error is completely eliminated here. Similarly, what will be the effects of this derivative controller KD? Because of this derivative controller there is a small change in rise time, overshoot decreases, setting time decreases, and there are also small change in steady state error. Small change means it can be increases or decreases with a small value. So after applying this PID controller, this is the output of this PID controller, and this is the error signal. Okay, so you can see here overshoot decreases, rise time decreases. All these are the applications of this PID controller. Now we are going to see PID stepwise procedure for manual testing. Actually this is not asked in the examination, but we are going to see it, that how you will going to apply this PID controller. Okay. So for this PID stepwise procedure for manual testing, first step is obtain an open loop response and determine what needs to be improved. The terms like rise time, overshoot, steady state error, you need to find out these terms, and what we need to be changed is to be detected. Then add a proportional control to improve the rise time. Then next step is add a derivative control to improve the overshoot. Then fourth step is add an integral control to eliminate the steady state error. The main function of integral control is to eliminate the steady state error. The fifth step is adjust the each of P, I and D until you obtain a desired overall response, referring to the table shown previously to find out which controller controls and what characterized. Then we will going to see the effect of this P, I and D controller. Then sixth step is it is not necessary to implement all three controllers P, I and D into a single system. For example, if a PI controller gives a good enough response, then you don't need to add D control to the system. Simple is better. Okay, again it is clear here that note that it is not necessary to implement all the three controllers which are P, I and D into a single system. If the PI control is sufficiently giving a response, then it is not must to add the D controller there, because simple is better. Okay, again here we are going to see so here you can see on your screen that this is the plant, and whenever you provide it a feedback loop, then we get a error, and if this error is sent directly to the plant, then the optimization of plant will be disturbed, or there will be some misfunction in the plant. That's why we put some controller here. Okay, that's why we put a controller here after the error is estimated and before sending it to the plant. Here the controller will be, it is in the form of PID or proportional controller, PI controller or PD controller. Okay, so these are the four types of this linear controller. I already teaches you that first type it is a proportional controller, then PD controller, then PI controller, and proportional integral derivative controller, which is known as the PID controller. So this is the simplest form of controller, which is proportional controller, where KP is proportional controller. It is connected between the plant and the input signal, and it's then send control signal to the plant. Advantages: it is a maximum overshoot increases and steady state error decreases. Here though the steady state error decreases, but there is a continuous presence of the steady state error which can be eliminated by applying the integral controller there. It is proportional plus derivative control. We see this today in this same lecture that along with this proportional controller, this derivative controller is also connected in the parallel, and then a combined signal is sent to the plant here. Okay, so this is the block diagram for the proportional plus integral control, where along with this proportional controller, the integral controller is connected here, and the combined signal is then sent to the plant here. So student, in the next section okay, again we are going to see this application of this PID controller is that it is used in regulation of processes in industries such as flow temperature regulator, pressure regulator. It is also used in a servo DC motor control, then linear position control. Dear students, these controllers plays vital role in the automation industries. Okay, now the theory part of this sub chapter is over here. From the next section we will see the numericals. So numericals about the finding of the error, then rate of controller output. For this we need to take some integral, study some integration and derivative form, then limits also we are going to need to study. Okay, So we are stopping here today. See you in the next section. Thank you.